Okay, so this is everything about the quarks. Are there any new questions in the meantime? Okay, so I showed this plot already. We have here this G1 structure function as a function of Q square for different ranges in X. But you see that it's not flat in Q square. So you have you would just have point-like interactions with point-like quarks. It would be flat in Q square, but here you see it's not. So we have scaling violation. This is related to the fact that you have to click again on the screen. Yes. Yes. So this is related to the fact that if you look at a certain Q square, let's say this is your quark, you look at it with a certain resolution, and then if you would increase your Q square, what you see is that this was actually not a quark, but it was a quark also emitting a gluon. It's just that before you couldn't distinguish them, it looked like one, and now this is the idea. So what this means that if you look at this asymmetry or this structure function and how it changes with Q square, you actually get sensitivity to gluons. And we were working with polarized electrons and protons, so we actually get sensitivity to the gluon spin. So we can access the gluon helicity distribution. Now this works in this electron-proton interaction experiments, but this process where you have the interaction of a photon with a gluon is much more suppressed compared to the process we looked at before, namely the interaction of your photon with your quark. So these gluons only enter at next to leading order, alpha. Now in proton-proton collisions, your gluons already enter at leading order. So you can have the interaction of a gluon from one proton with a gluon from the other one, which then go into one gluon, which itself then splits into a quark-antiquark pair, and these quark and antiquark pair can evolve to each one hadron, or can evolve into jets, or you can have the interaction of a gluon from one proton with a quark from the other proton, which then go to a quark and gluon, which each again fragment into a final state. So in these proton-proton colliders, you have much higher sensitivity to gluons, and you can look at different processes such as inclusive jet production, dijet production, pion production, or photon production. Even in the electron-proton interaction experiments, the gluons in the exclusive regime enter like at next to leading order only. You can increase your sensitivity to gluons by looking at the production of heavy quarks or or hadrons with high transverse momentum. So these studies are also done. Now, if we look at, we want to access the gluon helicity distribution in proton-proton collisions, we can, for example, look at the production of two jets. And again, the same, we construct the asymmetry. And this asymmetry is then again sensitive to your parton helicity distribution, each for each proton divided by the corresponding spin-independent parton distribution. And this sensitivity actually to the type of parton that you're probing depends on different aspects. What you have here is the invariant mass of your two dijets divided by the center of mass energy. And you see that at low mass of your dijets, you're mostly sensitive to the interaction of two gluons. At higher center of mass, at higher invariant mass of your dijets, you're sensitive to a quark from one proton and a gluon from the other proton. And on the other hand, the interactions with two quarks from each proton are much reduced. There are different panels here, and these different panels, they just correspond actually to the different directions of your two jets. And again, as we saw before for the production of W, there we were looking at the direction of your lepton, and we were probing different regions in X. Now here, you can look at the different directions of your jets, and as such, probe different regions in X. So here you have each time this pseudo-rapidity of your two jets that is indicated. So in the case that one jet goes into the end cap of your detector for star, this is now the configuration, and the other one goes in the central region, you access two regions in X that are actually partially overlapping. If your two jets goes in the forward direction, you get two regions in X that are quite well separated. So depending on the direction of your jets, you get again sensitivity to the regions in X that you are probing. So here you see an example of this dijet double spin asymmetry, so where your two protons are polarized. So in one case, you have the two protons spin aligned in the same direction minus proton spin aligned in opposite direction. And this is for different regions in pseudo rapidity of your jet. So this is for measurements by the star experiment at different periods in time. And so using the different available data, so again, phenomenology groups try to pinpoint the contribution of the gluon helicity with respect to the proton spin. And so this is again the same group, DSSV from Argentina and people from now in Germany. So you have here the integral over of the gluon helicity distribution over the range in X, where the range in X in this here goes from 0.05 to 1. So it's nearly the full range in X minus the very low X region. And here you have the integral over this very low X region. And the wider the region, the higher the uncertainty, because it just means like the larger the possible range of values for this gluon helicity distribution. So in green cyan, you have the first extraction. This was mostly based on EIS experiments. There is some very preliminary data from the Higgs proton-proton collider, but not so much. And you see that this EIS experiments, because of their limited range also in energy, they really didn't manage to put a lot of constraints on the gluon helicity contribution to the protons. Then adding data from proton-proton collisions, you see that the uncertainty, at least for the higher range in X integration, is already much reduced. We go from this possible range to this possible range, so that's a huge reduction. And now there is this very preliminary data combining all data from RIC up to 2022, where you see that the extraction here really limits the possible range in this integral. And what this shows here is that for X above 0.05, the gluon helicity is positive. So it means that your gluon spin is aligned with your proton spin, and that its spin also contributes quite substantially to the proton spin. So we have the quark spin and also a positive contribution from the gluon spin. In the lower region of X, we definitely still need to constrain the data better. But this is a second piece of the puzzle that's becoming a bit clearer. We get a non-zero gluon helicity contribution for X above 0.05. Now for the future, concerning quark and helicity spin contributions. So there are new experiments at class, for example. So here you see in all these colors the existing world data for the asymmetry on the proton as a function of X. And then in black, you see a preliminary measurement for class 12, where they only use a statistical uncertainty, but you really see that in this high region of X, so this valence region, this is where class can contribute. The uncertainties are, at least the statistical ones, are really much reduced. And then you also have a measurement on deuterium. So deuterium is a proton and a neutron. So by doing this, you learn also about the structure of the neutron. And you see that also here you get a much more precise determination. So this is something to follow up closely. So these were results shown only a month ago or so. So that will be really nice. And then the big project for the future is the electron-ion collider, where we will have an electron beam and a proton beam. And one of the key contributions that are planned for this new experiment is to try to disentangle the different contributions to the spin of the proton. So okay, time goes really fast. So I will try to go a bit faster here. So the idea of this electron-ion collider is that it will be based on the RIC accelerator that stopped taking data this year, and to make space actually for the EIC. So the EIC will use one of the hadron rings, and then a new electron ring will have to be built. And so the hadrons will have different energies ranging from 100 to 275, and also a bit lower possibly. And the electrons will have in the first step energies from 5 to 10 GeV. It can maybe later be upgraded to higher energies of 18 G. So one can get a different center of mass coverage depending on your beam energies. And so we will have longitudinally polarized electrons that will collide with longitudinally or transversely polarized protons, longitudinally and transversely polarized helium. And both for the hadron and the electron beam, we aim at a 70% polarization. And then we will also have a whole series of unpolarized ions up to uranium. And this is also really interesting because you can learn about nuclear effects, among others. Okay, so there will be 2 interaction points, and at one of the 2 interaction points, we will have the first detector, which is EPIC. I will say a few words about this. Yeah, let me immediately go there because I don't think. So this is the EPIC detector. So this, the central barrel at least, so it will be like 10 meters long and 5 meters in diameter. It will be a full coverage in phi angle, and then a coverage in pseudo rapidity, so linked to the polar angle of your produced particles, going from -4 to 4. So which corresponds to a polar angle between 2 and 180 degrees. So you have the hadron beam entering from the left, the electrons enter from the right. They will collide in the middle, and then a whole series of newly created particles will have to be detected in addition to your scattered beam electron. And in order to do this, well, you need different types of detectors. So in yellow here, you first want to really pinpoint down the point of interaction. So you need very precise detectors there. And you want to reconstruct the tracks of your particles. So again, you need precise detectors. And you also put in a magnetic field because your charged particles will be bent in this magnetic field. And from this bending, you can reconstruct their momentum. And I'll say a few words more about this a bit later, because this is, well, it's useful by itself, but it's also useful for other aspects. Then in green, you have the detectors which allow you to identify the different types of hadrons, so pions or kaons, protons. And then if you want to reconstruct photons and the electron energy, you have in red the electromagnetic calorimeters. And then we have in blue the hadronic calorimeters in order to reconstruct hadrons, for example, neutrons, but also in order to reconstruct the energy of charged hadrons, which can always help you in addition to your track. So that's basically the idea. For the central detector, but we not only have a central detector, but we always also have a very far forward and far backward system. So I said this barrel is 10 meters long, but then taking into account this far forward and far backward detectors, you're at 80 or 90 meter long detector. And so why do you need this far forward and far backward system? So first of all, forward is along the direction of the hadron. So your hadron beam goes like this. It's just a convention. So in this region here, in the far backward region, you place additional detectors for the case that your beam electron is scattered under a very small angle. If it's scattered on a very small angle, you will not see it in your central detector, but we'll go very close to the beamline. So if you put detectors far away, you might see it. So you can do interesting physics there as well. And then I told you that we always have to normalize our count. So you need luminosity determination. So you put also your luminosity monitor far away in the far backward. And this will be measured by detecting the Bremsstrahlung that is produced. And then in the other direction, you have also a series of detectors. And these detectors are there in order to detect hadrons that have been produced close to the beam line. Or if you had your proton coming in, it interacted but didn't break up. So when you look at exclusive processes, then it will receive a little kick, but it will not be seen in your central detector because it will not receive a large enough kick, and it will go again quite close to your beam line. And there you can have a series of detectors here to reconstruct these scattered proton or newly produced particles that stay very close to. And you also have something alike for neutral particles. Okay, so the idea is, so as I said, Rick stopped taking data this year and now starts to make place for the new EIC project, and we expect the first collisions 9 years from now, if everything. Now, why is this such a nice and interesting project for people who want to do hadron structure studies? Well, here you have the coverage in Q-square and X-Björken of the past and existing experiments. So you have all the open symbols are these fixed DIS polarized experiments. So you see that they're located at quite high X, and they don't actually span such a large region in X and Q square. And then in color, you have the Phoenix and star experiment, which again are polarized, but you see they also only have a limited range. They go a bit lower in X and they go up to higher Q square, but it's more a line. It's not like a full region. Now with DIC, the idea is really to cover up this whole region here, more or less. Okay, so this is really nice for the EIC. Now, at the EIC, we can do again the same type of measurements as I discussed. So we can look at these inclusive measurements where you only detect the electron. So you need a very good tracking, and actually also your calorimeter helps you a lot there to improve the reconstruction of your electrons. And so this is for the third time now, this figure with the world data of G1. This is what we have now, and this is what we will have with the EIC. So this figure here is this region here. So you see that with the EIC, we will go much higher in Q square, up to 10 to the 4th, compared to 100 maximum nowadays. And we will go to a much lower value of X, so down to 10 to the -4. And for the existing regions in X, we will have a much larger leverage in Q square. So this is really nice. And this will really help us to pinpoint down the gluon distribution. So this, you don't see it here because it's too light, but this is the current uncertainty. And then the different colors afterwards is by adding. So this is, yeah, we really don't see it. This should change. So it goes from here to here. So it's huge uncertainty. And then with the IC, including different energies, you can go down to a very good determination. Be careful that we only go down to 10 to the -4. So this is just an extrapolation. So you should only consider this region here. So this will be really nice for the gluon distribution, the gluon helicity distribution. Now I said we can study the gluon helicity distribution very nicely using a proton, but we can actually also learn something about the gluon distribution or the gluon helicity distribution inside the neutron. And for this, you typically use a helium target because the internal configuration is in 90% of the time such that the two protons inside your helium have their spin anti-aligned and your neutron has its spin aligned. So what you're actually effectively studying is the spin structure of your neutron. So again, you can make measurements but on your helium target detecting the scattered electron. But what we will also be able to do with the EIC is to, in addition, tag the two protons. So if you have your your photon interacting with one of your nucleons, well, the one you interacted with will break up and will scatter, while the two other ones that were just sitting there will inherit from the original momentum of your helium and will stay quite close to the beam lines, although they will get some. And so these two particles that did not participate in the hard interaction, you can then detect them in your far forward system. Okay, so that's the idea. I think that's nice. I like that one. So yeah, that's just what I explained. So also here, so then we can really learn a lot about the G1 structure function for the neutron. So the dots here are the existing well data, again, using the different DIS experiments, such as those at Jefferson Lab. And then with the EIC, we can really extend the range a lot. And then you have a similar plot as for the proton. We go from this coverage to this coverage, which is a huge difference and a huge improvement. Also for the different quark helicity distributions, so we will be able to make the same type of measurements as I discussed before. So you detect your scattered lepton, and then in addition now we have to detect the scattered hadron, so we need detectors to identify the hadron. So as before, we have our tracking detectors in yellow and the calorimeter for the reconstruction of the electron. And then for the hadrons, we will use again the tracking system in yellow. And then we will use different particle identification detectors, which are shown in green. And the way they work is that you use some material where in this material, your charged particle travels faster than light in that material. And if that happens through the passage of your particle, light cone will be produced. And this light can then be detected through photon detectors. So that's the idea. So you have here your particle that is created, your charged particle. It travels through the different detector components. Here arrives at the particle identification detector where it travels faster than light in that material. For example, you can use aerogel, which is a very light solid element. And then cone of light will be created, which will expand and be detected here in the different photon detectors. And the angle of the cone of the produced cone, or the opening angle of the produced cone, is inversely proportional to the speed of your particle. So we can already reconstruct its momentum because of the bending in the magnetic field. We here learn about its speed, hence we can know its mass. And once you know the mass, you know its identity. And here you see how well we can identify the different hadrons. So this is the opening angle of the produced light cone in this aerogel as a function of the momentum of the particles. And you see that distinction between electrons and pions is not so easy because pions are light, but you can distinguish a bit. And then between pions and kaons and protons, the distinction works actually quite good up to a certain upper value in moment. If you want to give even higher in momentum, you just use different types of materials. So depending on the type of material, you can scan different regions in momentum. Okay, so these type of detectors based on this emission of light cones of Cherenkov light are here and here and here, and they work well for particles with a momentum above, let's say, 2 GeV, but for very low momentum, you want to use detectors that measure the time of flight or time of traveling of your particles. So what you do is that you have a signal. So at the moment of your interaction, you have a clock telling you, well, now there is an interaction. Then in this time of flight detector, there's another signal and that says, well, the particle arrived. So you already have 2 points in time. And then with your tracking system, you can reconstruct the track of your particle, so how long it travels. So if you just divide the length of its traveling by the time it needed to travel, well, you get its velocity. And so again, using the momentum that we had obtained thanks to its bending in the magnet, you obtain, again, its particle identification. And here you see for regions in the central, well, in the barrel and the end cap of the detector, you see how well you can, again, as a function of 1 over the speed of the particles, you see how well you can distinguish electrons from pions, from kaons, and from protons. And this works well, you see, in this low momentum region. So in the end, this is the region with DIC or d-epoch detector, but we will take data, and this is the coverage from the different particle identifiers. So that's all set. That's nice. And so then we can perform our measurements and our studies. And here what you see is, so the Y scale has no meaning. You just have to look at the coverage in X, which is the X scale. The different colors show you the coverage in Q square. And this is now for the highest beam energy. So you see that we can obtain data with this highest beam energy down to 10 to the minus 4. So this is something we should then be able to do with the AIC. And again, then you can make studies and see how much the uncertainty on your different quark helicity distributions gets reduced. And you see that the impact of the AIC is substantial. And here for the strange quarks, we are happy to have counts again, and we can sensitivity with strange quark distribution. Okay, so this was for the one-dimensional imaging of the spin structure of your proton. So you just scan the structure along the longitudinal momentum fraction. But we can extend this and really have a 3-dimensional view of the spin structure of our nucleon and of the structure of your nucleon in general. Because there are different aspects to the different dimensions of your nucleon. So, and the maximally available information is contained in so-called Wigner distributions. And these Wigner distributions, they provide or they contain information about the distributions of quarks and gluons, again, as a function of their longitudinal momentum fraction, as a function of their transverse momentum, and as a function of their transverse position. Now, from these Wigner distributions, we basically don't know anything, but if you integrate them over transverse position, you obtain so-called transverse momentum dependent Barton distribution functions. So they tell us what the probability is to find a quark and a gluon as a function of its longitudinal momentum fraction x and as a function of its transverse momentum. And you have two components. Let's say that the longitudinal direction is the z direction. Then this transverse momentum has an x and y. So we are at three-dimensional picture of the nucleon. And you can study these again in the same inclusive DIS productions, but now taking into account, in addition, the transverse momentum of your produced hadron. And through the existing data that we saw, like from Hermes and Jefferson Lab and so on, they obtain already first very model-dependent pictures, though, of, for example, the distribution of your up quarks for different values of x as a function of these two transverse momentum components. This is now for the case where your nucleon is not polarized, but if you would now transversely polarize it, then you would see a shift to the right for your up quark. So your photon here is entering your screen. And so you would have a shift of your up quark distribution to the right and for your down quark distribution to the left. So by polarizing, you access different elements and you become sensitive to this type of distribution. Now, on the other hand, if we go back to our Wigner distributions and we integrate them over transverse momentum, then we obtain so-called impact parameter dependent parton distribution functions. And they tell us what the probabilities of finding a quark or a gluon as a function of its longitudinal momentum fraction x and as a function of its transverse position. And where your transverse position, again, has an x and y component. So again, we have a three-dimensional view. And these impact parameter dependent PDFs are related to so-called generalized parton distributions that I will discuss tomorrow. And these you can, for example, access in exclusive processes. So you again look at electron-proton scattering, but your proton does not break up. And you produce typically one or maybe two new particles, such as a photon or a whole meson or anything you actually like. And again, there have been like first measurements, and from these we have first very model-dependent pictures. So here you see the distribution of an up quark with a longitudinal momentum fraction x of 0.25, and here you have the two position components. And here you say the same, but for up quark with a much smaller longitudinal momentum fraction. So it shows you that quarks with low fractional momentum tend to spread away further from the center of your nucleon compared to quarks with a higher momentum. There are subtleties in this interpretation, but it's to give you an idea. And again, if you would transversely polarize our nucleon, we see a shift for the up quarks in one direction and for the down in the other direction. And so again, here the idea is to perform different measurements to really try to understand the different distributions. And both of these generalized parton distributions and these transverse momentum distributions, they are related to the PDFs if you integrate over transverse momentum or if you look at a certain kinematic. And these ones you all know. Okay, so let me now first concentrate on the left side of the figure, so where we access these transverse momentum dependent parton distribution functions, or TMDs. So far, we have discussed the helicity distribution. So you look at the distribution of longitudinally polarized quarks inside a longitudinally polarized nucleon. You know the standard PDFs where you look at unpolarized quarks into an unpolarized nucleon. Now, in addition, I did not discuss this, but you can also have the distribution of transversely polarized quarks into a transversely polarized nucleon. And these are different from these helicity distributions, formally because rotations and translation don't commute in QCD. You can look at it like this. You have your proton that is polarized transversely. You make your measurements, you boost it. That's it. Now the same, but you first rotate your nucleon, you boost it, and you get a different picture because of the boost. So image that sometimes is used. You do with it what you like. But okay, now if we also take into account transverse momentum, then we get a whole series of additional distributions. So for example, you can look at the distribution of unpolarized quarks into a transversely polarized nucleon. But there, in order for this to happen, you need your quark to have transverse momentum. And you actually probe the correlation between the transverse momentum of your quark and the transverse spin of your nucleon. And then you can also look, for example, at the distribution of transversely polarized quarks into a unpolarized nucleon, and you then actually probe the correlation between the transverse spin of your quark and its transverse moment. So really, by looking at different types of distributions, you can actually either probe spin-spin correlations, as we did with the helicity distributions, or you can probe correlations between the transverse momentum of your parton and the spin of your nucleon, or the transverse momentum of your parton and the spin of your parton. Okay, so there are really different types of distributions that you can access. And the way you can access them is by now also taking into account the transverse momentum of your produced hadron. So this transverse momentum of your produced hadron contains on the one hand side the transverse momentum of your quark while it was in the nucleon. You have your quark inside your nucleon. It has a transverse momentum. Then you have your photon here along the longitudinal direction. This photon will interact with the quark. The quark will absorb the photon. Since the photon has no transverse momentum, after the interaction, your quark still keeps the same transverse momentum. And then this quark will start to evolve into a final state hadron. And this evolution from the struck quark into a final state hadron also comes with an additional transverse momentum. So your transverse momentum of your hadron reflects the contribution from both of these transverse momenta. Okay. And so we get now our parton distribution functions as a function of x, as we had before, but now also as a function of this transverse momentum of your quark. And then we get fragmentation functions as a function of z, as we had before, but also in addition to this transverse momentum acquired during the hadronization. And as before, we get also a dependence on q squared. But this dependence is different than the one we had before. It's more complicated, but it's there too. And as before, we can have a longitudinally polarized nucleon. You can transversely polarize it, and then your quark can be longitudinally polarized or transversely polarized. So nearly any type of combination. Okay. So if we now look at the DIS cross-section for the production of a single hadron, this is the full expression, which is huge. Now, there are different terms that appear depending if your electron beam is polarized or not, and depending if your photon beam or target is longitudinally or transversely polarized. In addition, each of these components, let me, for example, here, they come with a certain angular modulation. And there are two angles that are important. Is the angle of the plane formed by your incoming and outgoing electron, and the plane formed by your virtual photon and your produced hadron. So that's one angle. And then the other angle is the angle between your lepton plane and the transverse polarization of your nucleon. Okay? So it looks complicated, but in reality, you have each of these elements, first of all, appear or do not appear depending on the polarization state of your beam and of your target. And then they all have a specific angular modulation. I'm going to skip this. And so the amplitude of this angular modulation, this is the one that gives you access to these TMD PDFs convoluted with this TMD fragmentation. So by extracting these amplitudes, you get access to different types of TMD PDFs and TMD fragmentation. And Most of the time we look at unpolarized hadrons that are produced. There are some exceptions, like if you produce a lambda through its weak decay, you can, from the angular distribution of the decay products, you can reconstruct its spin state. But in general, our hadrons are unpolarized, but that's okay. Like we can look at different types of fragmentation functions that produce an unpolarized hadron. So here, in this case here, you have a fragmentation function describing fragmentation of your transversely polarized quark into an unpolarized nucleon. And this will combine with certain types of TMDs. And then you also have our normal unpolarized quark into an unpolarized hadron that will combine with all of these other TMD PDFs. So when you perform your measurement, you have a combination of one of these TMD PDFs with this fragmentation function, or one of these TMD PDFs with this fragmentation. And these fragmentation functions, I only listed two, because we usually only look at unpolarized hadrons, but in the same way as you have for your TMD PDFs, you have different configurations for your hadrons. So transversely or longitudinally polarized hadron evolving to an unpolarized transversely or longitudinally polarized hadron. Just that the point is that we cannot really reconstruct most of the time the polarization state of your produced hadron. These fragmentation functions, they're not so easy. This is like a cartoon where you have your struct parton, and this is all the hadrons that can be produced from it. So you see it's really not easy and not clean, and you need to extract this from the data. So as before, we can look at lepton-proton interactions where you detect a scattered lepton and a produced hadron. That's nice. For the TMD PDFs, we can look at proton-proton interaction to Drell-Yan production. So your quark antiquark puts annihilated to a photon. This photon then decays into a lepton antilepton. So that teaches us about our TMD PDFs. Here for semi-inclusive DIS, we have the TMD PDF and a TMD fragmentation function. For electron-positron annihilation, as before, we can look at fragmentation functions from each of the quarks coming from the virtual photon in the electron-positron annihilation. Now, the problem, though, here, contrary to before, is that because we have transverse momentum, we cannot use proton-protons going to two hadrons, because you would break factorization. The problem is that you have color objects. So the problem in summary is that here you have color objects and here you have color objects, and they can talk to each other, and that messes up the whole factorization, becomes a mess. Here things are clean, here things are clean, and here things are clean. Here there are some exceptions, but I will mention them later. Okay, but that's, yes. What is also important for the TMD physics is that it's not sufficient to just have transverse momentum. Your transverse momentum needs to be small with respect to your Hart scale. Then you are really in this TMD regime. If you go to higher transverse momentum, then you actually can just use the collinear standard PDFs. But then for people who know, not at leading twists, but at sub-leading twists. If you don't need really transverse momentum, intrinsic transverse momentum to describe the transverse momentum distribution of your produced hadron. So just for you to know, the TMD region is only in the region of small transverse momentum. Okay, there this physics. So there are different experiments again over the world studying this TMD physics. And again, I added here Bell and Bell 2 because of the fragmentation functions. Okay, so let me start with electron-proton interactions, and let me show you how you can, but I think, so it's till what time do I have?
Stay until 11:30.
11:30, okay. So one of the measurements that we can make is to access this transversity distribution. So you look at the distribution of transversely polarized quarks into a transversely polarized nucleon. You don't need transverse momentum, but you can include. So you again construct your symmetry, number of hadrons produced in this configuration minus this one. And this asymmetry comes with a certain modulation, namely sine phi of these two angles I described before. And then your amplitude is a sum weighted by the charge square of this transversity distribution and the fragmentation function, they call it the Collins fragmentation function, that describes the fragmentation of your transversely polarized quark into an unpolarized hadron. Yes. So here you see an example of such an asymmetry that has been measured. And what you see, so you see it here as a function of x, z, and the transverse momentum of your produced hadron. So for positive, negative pions and positive and negative kaons. Now, if we look at the high X region, we're in the valence region. So you start with a nucleon that has 2 up quarks and 1 down quark. So you already have more U quarks than down quarks. And then, as I showed you, you have this, each contribution from each quark favor is weighted by the charge square. So in this high X region, it's more likely that you are actually scattering off a U quark compared to a down quark. So what we see here for positive pions is that, let's say, we assume we were indeed scattering of a U quark, and this then evolves into a positive pion. So you have your transversity distribution of your U quark that is studied here times this fragmentation function, telling you what the fragmentation is of your transversely polarized quark into an unpolarized. For the pi minus in this region, we again have our U quark, and then this fragmentation of your transversely polarized U quark into an unpolarized pi minus. And what you see is that they are opposite in sign. So this tells us that these two fragmentation functions going from U to pi plus or U to pi minus are opposite sign. Okay? So that's one thing we can learn from the data. And one way to understand this is through the Arthur model. So let's focus on the left side here. We have our incoming electron, our scattered electron. Here we have our virtual photon. And then we have here our photon that is transversely polarized. So the polarization here along the screen. And we have our U quark that is also transversely polarized with its spin aligned to the spin of the photon. Okay, so the photon arrives. The quark will absorb the photon. It will flip its spin in the plane. So this is after the interaction. Then your quark, the green here, will move away from your nucleon up to at some point it's so far that a quark-anti-quark pair are formed out of the vacuum. Yes? Yeah? Okay. What we want in the final state is a positive pion. So that has spin 0. So you want the two quarks, valence quarks, forming the pion, you want them to have their spin anti-aligned. Okay? So you have your Schroer quark moving away, your quark-anti-quark pair from the vacuum. You have to respect the vacuum quantum numbers. So you have your orbital angular momentum in one direction and your quark spin in the other direction. And this quark will then combine with this anti-quark from the vacuum to form spin 0 particle, which is a pion. Yes? Now, we have here angular orbital momentum going downwards. So it's like this quark-anti-quark pair are like turning like this, coming out of the screen back in. Now this parton will combine with this. So this object will inherit from the orbital angular momentum from your quark antiquark vacuum. So you will get your pi coming out of the screen. Yes. And this corresponds with the positive asymmetry that we see for pi plus. Okay. Now we are left with this. And now we can play the same game with this one. So we started with a U quark, and we want to make a pi minus now. So you need, so this was U anti-down quark. Now we have a down quark. Down quark is perfect for a pi minus. And then you just repeat the same picture, but everything reversed. So your orbital angular momentum will be in the opposite direction. So your pi minus will enter. And this explains in this model the opposite sign for pi plus and pi minus. Okay, so this is just to give you some intuitive idea. What we see for K plus compared to pi plus, again, in this valence region, is that your K plus is larger than your pi plus amplitude. So again, assuming that you were scattering over U quark, this would mean that this fragmentation function for U going to K plus is larger than for U going to pi. So these are like elements you can get from your data, just to get some intuitive picture. Now then afterwards, like you combine all the existing data, give it to phenomenologists, and then you get a more precise picture. And what you see here is the transversity distribution for the U quarks, which is positive, and for the down quarks, it's negative. So this would mean that for transversely polarized nucleon, the up quark has its transverse spin aligned with the spin of the nucleon, and the down quarks have it anti-aligned. Actually, just like we had for the helicity distribution. Okay. Then we can look at another asymmetry, namely one that now comes with a phi minus phi s modulation. And now we get access to, well, our standard spin-independent fragmentation functions times the so-called Sievers function. And the Sievers function describes your distribution of unpolarized quarks into a transversely polarized nucleon. So now you get a correlation. You're proving the correlation between the transverse momentum of your and the transverse spin of your nucleon. And in the beginning, it was actually thought that this function would be 0. But then they realized that what is really important is that there are final state interactions. What this means is that your quark, after that it got struck and moves away from the remnant of your nucleon, while the remnant of your nucleon and your quark still talk to each other. That's really important. Otherwise, this function would be 0. And as you can also understand, since you're probing correlation between transverse momentum of an unpolarized quark and the transverse spin of your nucleon, maybe intuitively can understand that this function requires a non-zero orbital angular momentum of your. So here we get the results. Again, the same configuration for pi plus, pi minus, k plus, and k minus, a function of x, c, and p perp. And what we see now is that we get a positive value for pi plus and something consistent with 0 for pi minus. Now, intuitively, again, just to give you some picture, we can try to understand this. So here you have again a beautiful picture of your proton with your proton polarization sticking out of the plane. It's again transversely polarized. You have here your incoming and scattered electron, your virtual photon, and this will interact with U quark inside your nucleon. And let's imagine that your U quark is turning around anti-clockwise like this. Now you have to know that if the photon and the quark are moving towards each other, the probability of interaction will be a bit larger than when the proton and the quark are moving away from each other, because there is a z component in your current calculations. So it means that if your quark is moving like this, it will be a bit more probable that your quark will interact here with the photon compared to here. Okay? So your quark is turning around, interacts with your photon, absorbs the photon. Your photon has only longitudinal momentum. So normally, your quark would just inherit the longitudinal momentum of your photon, knowing that this is a lot of energy. Here we have a beam. Here we just have a target. Your quark would just inherit it, move away, more or less in a straight line. But the remnant of the proton doesn't want the quark to go away. It's like, please don't go, stay, stay, stay. And so there will be this attractive interaction of the rest of the nucleon to trying to keep the struck parton close. And because of this, your quark will actually be bent downwards. It will not just go in a straight line. And this picture corresponds to having a positive amplitude for the pi plus. Now, on the other hand, if your down quark rotates in the opposite direction, you will have like a larger probability of interaction here. Your quark will move, your down quark will move away of the nucleon. The rest of the nucleon doesn't like to see the quark go away. So again, there will be final state interactions and a bending. And so you would get a bending in the opposite direction. So for the down quark, an amplitude in the negative amplitude. Now, what we see for the pi minus is that we get something consistent with 0. We know in the pi minus is down anti-U quark. Now we're at high X, so it's quite probable to have an interaction with the U quark. On the other hand, the fragmentation of a down quark to a pi minus is also easier than a U quark to a pi minus. So here you would have a combination of U and D quarks, and they would then cancel each other. You will get 0 amplitude. Okay, so this is again some intuitive interpretation, but then again, if we give everything to all the data to the phenomenologists and they perform a decent extraction, we indeed see that the Sievers distribution for the U quarks is positive, while that one for the down quarks is negative. For the anti-U and anti-D, it's not inconsistent with 0. Okay? Now, in the lepton-proton interactions I just showed you, we can study the Sievers distribution, and I've just talked to you about the final state interactions. And these are attractive because the remnant of the proton doesn't want the quark to go. We can also study the Sievers distribution by looking at Drellian production. So you would have one of the protons transversely polarized. You make it interact with another proton. The two interacting quarks of each proton would annihilate in a virtual photon, which would then decay into oppositely charged leptons. Now here, you also have interactions between, well, something similar to final state interactions, but it's a bit different. You have like one proton and another proton, and they're like forced together, and they don't know each other. They don't like each other so much. So they would have rather like a repulsive attraction between each other. And this is indeed what you see. So there you have initial state interactions because it's before the hard interaction. And there, this interaction is repulsive. And because of the difference between the attractive and repulsive interactions, difference between initial and final state interactions, sorry, you will have actually, or you expect an opposite sign for the Sievers distribution in electron-proton scattering and in Drellian. Now, very formally, this goes with the insertion of a gauge link that you need to make your calculation of your elements gauge invariance. And in the CD's case, your gauge link goes towards positive infinity. Then, while in the Drellian case, you go towards negative values, but that's like very technical. But there is to this whole blah blah story, there's a formal calculation. Okay, so there have been measurements in hadron-hadron collisions in order to try to access sieverts in Drelian. So they used the transversely polarized proton and a pi minus beam. So this is the COMPASS experiment. And then they looked at Drelian production. So here in this drawing, you have a U anti-U producing oppositely charged ions. So this is what they looked at. And again, as before, where you can construct different angles, you can write out the full cross-section, and you have different contributions with each a different angular modulation. And these distributions that are probed corresponds to the one for the pi minus, and this one here for the proton. And what we see here, we have one indeed sensitive to the Sieverts distribution. So by accessing this modulation here, the Sieverts distribution was extracted. So they have one data point for the Drelian measurement. And this was then compared to models based on the TDS data, where in one case, these models do include the predicted sign change. And here in this part here, these same models pretend there is no sign change. And what you see is that your data seems indeed like compatible with the fact that there is a sign change, which is a good thing, because otherwise there would have been something fundamentally not understood in our description of QCD. We have done also these measurements again at STAR, at Drake. So there also, this is one data point they extracted for the production of theta 0. And then they also looked at the same, but now looking at W production. So there they have more data points here. This is as a function of the rapidity of your produced W. So again, related to this, the angle of production. And these data points are compared to models that do include sign change, which is a full line, and that do not include the sign change, which is a dotted line. And again, the data is compatible with the sign change. So that's really nice. Okay, so this is another exercise that we can do. And then I'm going to talk about the last one, the last distribution from the TMDs. And this is the Bohr-Mulders distribution. So where we look at transversely polarized quarks inside an unpolarized nucleon. But what we probe here is now the correlation between the transverse spin of your quark and the transverse momentum of your quark. And I said it's like unpolarized hadrons, so you can actually do this type of measurements even at facilities that don't have any polarization, such as the LHC. So even though the LHC has nothing of polarization, we can do spin physics. Well, like before, you can probe this in electron-proton scattering or in Drelian. As before, you can have you expect a sign change because of the difference between initial state and final state interactions. Now, this Bohr-Mulders distribution is really nice. I mean, in the end, there are many distributions. Everybody has its favorite. There is no real reason for it. So when I say it's nice, it's just like my own preference. So I think it's a nice one. Again, you just look at the cross section. Here, nothing is polarized, but you can look at the angular distribution of your hadrons. Now, it's nice, but it's also a much more complicated one because you cannot just construct asymmetries. And so what you do is you want to access this modulation here, but contrary to before, you cannot do number of events in one state minus number of events. The other state, you just really have to look at the modulation, and you make your measurement of this modulation, but you actually want to access the underlying physics modulation. Now, going from there to there, a lot can happen. So you can have radiative effects of your electron emitting radiation, for example. In addition, your detector is always limited in acceptance. And so let's say this blue thing here is your detector, and these are the different bins. Well, what can happen is because of a infinite or finite resolution, sorry, of your detector, you can have migration from one bin to another, or even from things that would normally not be seen in your detector, you can have migration into your detector. And all these things you need to correct for, just to give you an idea. So this is a Monte Carlo simulation where, as a function of this angle phi of your hadron, you injected a distribution that was flat in phi. Nothing happens. Then you run this simulation through your detector, you reconstruct everything, and what you extract is this complicated curve here. It has nothing to do with your original one. So you can see that going from there to there isn't easy. And what was found here for this experiment, it's a fixed target experiment, is that you really need to do an analysis differentially in all your possible bins, and then using Monte Carlo techniques, you can go back from your reconstructed to your generated. So it's a nice one, but it's a complicated. So here you see the example of a measurement, and what I didn't say, I'm sorry, is that this modulation, so you have this Bohr-Mulder distribution times again this Collins fragmentation function. And if we now look at the data, so first of all, you see here for pi plus and pi minus as a function of different variables. The open circles, or sorry, squares are for deuterium, the closed one for protons. We see that we don't see any difference between protons and deuterium, which would mean that U quarks and D quarks, again being pi height x, they have the same Bohr-Mulder distribution. Now, starting from that point, you know, U and D are the same. If we now compare pi plus and pi minus, well, the pi minus is positive, the pi plus is negative. So you would have, let's say again at the high x, your U quark going to a final state hadron, but again, you have a transversely polarized U quark, so you have this Collins fragmentation function. So these data are again compatible with the fact that you get opposite sign for your Collins fragmentation. Okay, so I just mentioned it too, that you see that things are compatible with what we saw before. Now, I said we can also do this type of measurement or access the Bohr-Mulder distributions at unpolarized facilities, such as the LHC, so where we have 4 main experiments, CMS, Atlas, which are the 2 big ones, and then ALICE for heavy ions, and LHCb, which actually for B physics. But you can, at each of these experiments, you can also look at proton collisions and study something about the structure of your nucleon. So since we are with unpolarized hadrons, you can actually only access the standard PDFs and these Bohr-Mulders, TMD PDFs. And it's nice to look at LHC data because of the much higher energy, you probe a very different region in X. And I told you that for TMD PDFs, we have an evolution with Q squared, as you do for PDFs, but for TMD PDFs, it's much more complicated, and you actually have a non-perturbative part that you need to extract from data. So if you have a very large range in Q square, you can really start to study this evolution of Q square of your TMD, the evolution with Q square of your TMD. This is already nice from the LHC by itself regardless of spin. But in addition, so at the LHC, we can then now probe also these Bohr-Mulder distributions by looking at different modulations, and this has been done. And here you see the A2 modulation, which is sensitive to the spin-independent PDFs and also these Bohr-Mulders TMD PDF. And you see it here as a function of transverse momentum of your produced photon or Z boson. And you see in black different data points from Atlas, in blue from CMS, and in red from LHCb. And this is for different region in rapidity of your produced final state particles. Now, you see this compared to theory predictions. So here, the full line shows the contribution of both distributions, and then the dashed line shows the contribution only of the unpolarized PDFs. And as you can see in this region here at low QT, your Burmulder's contribution is dominant, and here your spin-independent PDFs is dominant. And what you see is that indeed, there seems to be a contribution here from your Burmulder's distribution according to the data. There is still an issue though, because there's an incompatibility between the Atlas and LHCb data, which are the red points. So these are just the very first pictures. If one wants to extend this, much more studies are needed. I think I have to stop because the other one is a new subject. Okay. It's still half, right? What? It's still half past. Still...
Yeah, let's stop here.
Okay. Are there any questions? I know this is a complicated subject.
Hello, thanks for the great lecture. I was curious about the final state interactions with the Sivers effect. Was there can you think of that as breaking factorization in a way? Is it breaking factorization at all, between the fragmentation functions and the PDFs? Is that with the final state interacting with?
So they no, because you can factorize it. So you don't break factorization. They do talk about non-universality in the sense that what you extract from one is not the same as the other. So if I showed you with the PP collisions and your TMD fragmentation functions, you have your PP collisions and your fragment and your used hadrons, and there it don't work anymore because you have breaking of factorization. And what would you extract from? If you would extract fragmentation functions from there or PDFs, you could not or TMD PDFs, you could not apply them in another process. So there you have really a total breaking of factorization and universality. But for Sivers, I would say a sign change is not a problem if we understand it. So I would not talk about breaking of universality, and definitely not a factorization.
I was also curious with the the fragmentation functions dependence on the transverse momentum.
Yes.
Is there an intuitive way to understand why the fragmentation process would depend on that variable? Apart from the well, you have your part. You have your parton. And from going to a parton to a final state hadron, a lot happens, right? So maybe you could even ask the question differently, why would it not acquire? How would it manage not to acquire transverse momentum? Because do I have, yeah, look at all the interactions that are happening and taking place. So not to acquire any transverse momentum if you get kicked around all the time or you're emitting gluons and you have energy exchange, I don't see how you would not. On the other hand, it would average out. It's true. So yeah, there's a lot of smearing and interaction. So this is how I would look at it. I don't know if Alberto has a better explanation, intuitive picture.
Distracted.
Okay.
What was the question?
No, if one has an intuitive picture of why you acquire transverse momentum in fragmentation, you have to, just because of all the interactions, right?
Well, yeah, anytime you split something there, that's one possible of interaction. You are imagining that nothing else is happening on the lower side. So you're just imagining that the initial quark is by itself. However, anytime you have an interaction, you have a transverse momentum. calculate the vertex, square it, you have a dependence on the transverse momentum. So easier to produce transverse momentum than it is to not do it. You have a lot of base space. Actually, it's pretty unlikely to produce something with zero transverse momentum.
That helps. Thank you.
The question.
Thank you for the good lecture regarding like when we are doing the transverse momentum and we are like when we are analyzing the transverse momentum regions like in DIS region, like if small momentum region, what are the things we need to consider like challenges in like small momentum region like longitudinal in the data collection?
So when you access the low X region, what you need to consider compared to higher X region when you take data. So coming closer then. So to access the low region in X,
You need, I don't know, how should I say? So for high X, you can just use a fixed target and a beam. Yes. For low X, you need much higher energy. So you would use beam collisions. And doing physics there in beam collisions or in beam fixed target collisions, it's,
I would say, very different.
the whole environment is quite different. You get issues with other problems. Usually when a fixed target experimentalist goes to a beam experiment, he has to learn a lot of things new and vice versa. I don't know if that really answers your question.
And what are the gaps in the table? What are the reason behind it?
This is physics laws, like some symmetries that have to be with.
Thanks for the nice talk. I just want to ask about why do people use Cherenkov radiation to distinguish particles? Can we use other phenomena or effects to do that? Or what's the benefits or advantages of Cherenkov?
It's clean, not too, so, okay. So there are different aspects, and we'll also not be able to fully answer your question because I don't know all the details. But so what you have here is your interaction, right? Then your particles evolve through the detector. You need different detectors in order to address different aspects of your experimental reconstruction. Yes. However, you produce here a particle. If you would, for example, have a heavy detector, your particle would interact with your detector. And by the time it would be here, it would not at all contain the original information of your interaction. So very close to your beam interaction point, you want very light detectors that do not disturb your particle at all. And so that's why here, for example, for vertex reconstruction, or track reconstruction, you would use gaseous detectors or silicon detectors, where the advantage of silicon detectors is the very high. That's typically like the first stage that you do, vertex reconstruction and track information or momentum. Then comes the next least disturbing detector, which is here, these Cherenkov detectors. So it's true, you just put like some light aerogel or gas, depending on your momentum range, your particle goes through and it's not really disturbed. However, then if you have your electromagnetic calorimeter, then your electrons and your photons are stopped and your hadrons will already interact much more than in the previous detectors. And then if you have the hadronic calorimeters at the end, there even your hadrons are stopped. So there is this consideration of trying to not have too disturbing detectors Now, afterwards, if there would be other technology than Cherenkov detectors, well, I know about time of flight. I know about the Cherenkov detectors for PID. I don't really know about other detectors that are as efficient. I mean, even in silicon detectors, you could look at energy deposition and distinguish from the energy deposition between these types of hard fluids, not as efficient. So these are some aspects you need to take into account. I don't know if I fully answered your questions, but okay.
Other questions or curiosities? Then I have one. On page 17, you were mentioning that Atlas is measuring something different from others. And it's interesting because also in
17?
70.
You mean for the Bourg-Mulder Australian?
Yeah, because also in unpolarized measurements, Atlas measures something different when they try to measure charm plus jet kind of measurements to access the strangeness. They measure something different from CMS. So I was wondering what is happening here in this for this observable. How they are different.
I have no idea. Not part of Atlas. I don't know what is happening. There is at the moment no also. So this is work from Alexei. He hasn't mentioned to me anything about this in particular. I don't know.
No, just here. You said that it's different.
Yes, but maybe they made a mistake. Maybe something is not understood. The point is that they are accessing the same variable. They're in the same rapidity region, but Atlas and LHC have different, and I don't know why. It's twice PP in a given rapidity range, so.
Okay, still seems compatible with the uncertainties to my eye, borderline.
But everything is, it is, even if you integrate, right? Once you integrate, yeah. But the problem is that it's all in the same direction. There is a discrepancy.
Okay.
Okay.
Nobody's jumping up to be chosen. So we can thank Charlotte again